In this video, we're going to start talking about beams as elements and how we design them and how we look at the forces within them to know what we have to design against. To do this, we're going to use a process called shear moment diagramming. And basically, using the cow here to illustrate, we're going to think about what's happening, for instance, in this cow's spine. And we're going to think in particular about how every little piece of the cow's body is contributing a shear load that the spine has to carry, a diagram that looks something like this. And because of where those shear loads occur and how far they occur from the supports or legs, the spine will also have to carry bending, and that'll be a diagram that looks like this. This diagram in particular starts to look a little architectural. We'll talk about why that is, and we'll talk about the relationship between the moment diagram and the form of the beam. So in the last set of videos, we talked about beam equilibrium, how we find reactions to ensure that a beam is in both translational and rotational equilibrium. That is always going to be the first step when we're trying to analyze or design a beam. In this next set of lectures, we'll talk about how we actually get into the beam, try to figure out how those external loads and reactions are resolved by internal stresses within the beam, and then we'll start to look at what we have to do to counteract those, to carry those across the span. So in this video, we'll start very sort of simply with looking at loads and reactions and what internal stresses have to arise within a beam for the beam to not only be an external but also internal equilibrium. In the next video, we will do a ton of examples, and then we will flip around and start to look at the cross-section of a beam and why the sectional shape of a beam is so important, why it matters more than, say, in a tension rod or a simple compression structure, those sorts of things that we've looked at before. And then finally, we'll look at methodology. We'll look at how we actually go in and select beams. This will use a mathematical principle called section modulus and a very simple but I think very beautiful formula called the flexure formula. And then we'll also do a ton of examples of beam design as well. To me, this set of videos, this lecture on beam design is really the kind of the heart of the structures sequence. It's where we get most architectural, where the structural form of beams gets derived mathematically, right, derived from physics, but starts to give us a library of forms that you see over and over again when you're out in the world looking at actual architectural structures. So I want to make sure that everyone grooves this and understands it. We'll do a ton of examples, and we'll have a couple of bonus videos where we go through and review and do examples, particularly of shear moment diagrams and beam design or selection, just to make sure we're on sure footing going forward, talking about other structural elements. So remember that we talked about two types of equilibrium in structural elements, particularly beams. There's external equilibrium, which we looked at in the last set of videos. How do we keep a beam in translational and rotational equilibrium? And remember, that had to do with figuring out supports for the beam that would balance out not only the vertical forces being applied to it, but the rotational forces that those loads imply to the beam. We hadn't yet talked about the beam itself or what it was actually made of, and now I want to kind of switch focus and really look inside the beam and see if we can figure out what's going on within the actual material of the beam itself. So switching from external equilibrium, where we have a nice simple rectangle, to internal equilibrium, where we're looking at actual material that has certain amounts of strength, but is also subject to actual failure, right? A little bit more involved. We're going to look at this second family of forces. In previous classes, we've mostly looked at compression and tension. We've designed structures where everything is axial. All the loads are happening along a structural element. And we're going to switch focus and look really at two in particular, shear and bending. Torsion will talk about just a little bit, but really what we want to get at is this complex phenomenon of bending, where we have tension and compression in a structural element at the same time. Shear and bending are primary internal forces. They both affect beams or spanning elements. Shear we've looked at very briefly before. It's the tendency of a material's particles or plane to slide past one another. We measure this just like we do weight in pounds or kilograms, and it is directly related to the magnitude of forces that we put onto a beam, the applied loads and also the reactions. Anything acting perpendicular to the beam's long axis is going to put the beam into shear. It's going to tend to make the planes of that beam slide past one another. Related to this, but a little bit more complex, is bending. Bending also results from putting a load onto a beam perpendicular to its longitudinal axis. Bending is actually a pair of forces. It is tension and compression in the opposite edges of a member. And we measure this the same way that we measure moment. We measure it in foot-pounds or kilogram meters. It's related to the external forces, but as we'll see, it is also related to where those forces occur on the beam. If you think about it, shear we measure in pounds, kilograms. That is just a factor of the magnitude of the forces that we're putting onto it and the reactions. Bending, we're interested in where those loads occur. And so if you think about it, we have not only the magnitude of the force, but we're also going to have a linear dimension to the level of bending, right? Feet and pounds, foot-pounds. These are, maybe not surprisingly, linked to one another. Because the magnitude of the force figures into both of these, shear and bending will always have a mathematical relationship. And the good news is that with some simple math and some intuition, we can think our way through the way a beam has to work and come up with some relationships between the level of shear in a beam and the level of bending. In particular, if we can locate and find the maximum shear value and the maximum bending moment under any loading condition, we can go ahead and use that in the next step to think about how we actually design beams. And the good news is for simply supported beams, this is usually relatively easy. We can look at the loads, we can look at the reactions, we can think our way along the beam, and using some basic math relationships between the level of shear, the level of bending, we can come up with some graphs that start to give us an indication not only of the way the beam is resisting those loads, but also what the magnitude of the stresses inside the beam will be. So think this through. Think of yourself as a beam. If you want to do a plank while we're talking about this, go right ahead. If you are doing a plank, the distributed load that you are carrying is your own weight. If you're maybe particularly eager, maybe you've got some barbells or something that you're putting on your back, but for the moment, let's just say that you're carrying your own self-weight across a span of anywhere from 4 to 6 feet. You will have reactions that you will feel in your elbows and your toes, and you'll have a set of internal stresses as well that if you think about it, you'll feel too. The shear that your body is undergoing is related to the total distributed load that you're carrying, your own weight, and its resolution in your shoulders and ankles. Your shoulders in particular, if you're doing a plank, you will notice very quickly that there is an internal stress that feels like your arms kind of wanting to slide past your torso or your chest. That is the shear force inside your shoulders that is helping to carry the load of your body down into your arms. A little bit more complex, though, is bending. And if you think about doing a plank, you will feel two different forces. Across your back, you'll feel compression. Your spine goes into compression to help carry the load. And across your front, your muscles go into tension, right? They tighten up trying to carry the load. You have both of these stresses acting within your body at the same time. And because, whether you know it or not, you're a simply supported beam in this configuration, you will have compression on the top, tension on the bottom. We'll talk about why this is a little more in the next set of lectures, but for the moment, know that when you're experiencing bending, or when a beam is experiencing bending, in most simple conditions, the compression is on the top, tension is on the bottom. Now, if you've ever done planks with a personal trainer, you will hear them say things like, get your butt down, flatten your back, things like that. That is because they are trying to maximize the amount of tension that your abdominal muscles are undergoing. If you do a plank that's more like a pike, like you see on the top, your body is acting more like an arch. More of your body is in compression, and that is not going to do your muscles any good, right? That is going to be carried entirely by your bones, which are going to get the full brunt of the workout. If, on the other hand, you have good plank form, right, your body is flat, then you will definitely feel that tension in your abs. Your abs will tire out after a little while. Your spine will still be in compression, but it'll be in compression paired up with the tension in your abdominal muscles that are helping to carry your load to your shoulders and to your ankles. So remember this as we're thinking about beams. Maybe remember it when we come back to arches, that an arch is really a bad plank. A beam is really a good plank. So let's look at what happens when each of these are in actual beams. And the first thought experiment I want to do is to take a beam that has a single load on it. Can be anywhere at this point, and it'll have two reactions, right? We've seen this from the last set of lectures. Depending on where that load is, those reactions might be equal. They might be different depending on how we move the load. But what I want to do in this video is actually think about what's happening inside the beam. So think about the beam as a series of slices. Think about it like a stack of crackers or a stack of cookies or something. When we push down on one of those slices, one of the cookies in the stack, what's actually happening to keep that cookie in line, to keep the beam together? We have an external load that's pushing down. We know that we've got external loads, but they're several slices away, so they aren't able to help necessarily in keeping that slice right there. The tendency of that slice is going to be to slip, right? To slide past its neighbors. That's the very definition of shear, and fall down, right? Not carry the load. What resists that is an internal stress, a shear stress. And for most materials, we can go look this up. We can see how good a material is in shear, what sort of capacity it has, and like tension or compression, we can measure the cross-section of the beam that we have, or we can figure out the cross-section of the beam we have based on the material's shear capacity and its cross-sectional area. Notice that in this case, we've got shear on both sides of the slice, and the shear resistance on those two sides is going to have to be equal and opposite to the load that's pushing down on it. Okay, now let's continue the experiment, but let's move all the way over to the last slice. And we're going to think about what's happening just a little bit inboard from that left reaction. We've calculated the reactions for the load, so we know that there is an external force, the reaction, that is pushing up, that has to resist the tendency of the load to push the entire beam down. And now if we dive into that slice, right, what we find, if we turn this into a free body diagram, ignore the rest of the beam, and think about what has to happen to keep that little slice just to the left of the beam in one position, what we realize is that there has to be an internal stress, right? A force that is within the beam itself, a shear stress that builds up that's going to be equal and opposite to that external force, right? This might be 20 pounds, 100 pounds, 50 kilograms, 300 tons, whatever, pushing up. As we go just a little bit inboard of the beam, we need to have an internal stress that matches that, that's equal and opposite to it. Think about this again, right? That little slice can be infinitely thin, or it can be slightly bigger. As we'll see, it can be any size up to the first load that we put on the beam. And for any of that, if we're just thinking about keeping that slice in place vertically, then all we have to do is match the reaction, the external force, with an internal stress. And the stress is going to be able to resist that force depending on how strong the material we're using is in shear. When we move along the beam, when we get past that first load, okay, now think about how we can keep this free body in position. we have an external force pushing up, we have an external load, pushing down. We're going to have an internal stress that has to be the differential between the reaction on the left and the load that we're applying somewhere in the middle. Now, it might go up or down depending on where that load is and how much magnitude there is, but there will be some internal stress to the right of that load that has to be different than any internal stress to the left of that load. We look at a free body of the beam, look at all of the external forces working on it, the load here, the reaction here. The difference between those has to get made up by an internal stress to keep this half of the beam in place, right, to keep it from moving up or down. We think through this using a tool called a shear diagram. So here, for the simplest possible loading condition, we have a load P that's at the midspan of a beam. So we can go back and do the reactions, but I think we've done enough by now that we can just assume that that load, if it's at the midpoint, will be equally divided between the two reactions, right? Reaction left, reaction right. So here we have P, here we have P over 2. The way we draw a shear diagram is we step back and we think about what internal stress is needed at every point along the beam to keep the beam in translational equilibrium, to keep it from moving in the y direction, up and down. So if we go just like a fraction of an inch to the right of that first reaction, we find that we have a free body diagram that has P over 2 pushing up, and therefore we need an internal stress that is P over 2 pushing down. That level of stress is going to stay all the way through that first half of the beam. No matter where we take that slice, if we ignore everything to the right of the slice and just treat this piece as the free body diagram, we are always going to have just one external force working on the beam. That's going to be the reaction here, P over 2 pushing up. And so every slice we take in that beam is going to have an internal stress of P over 2 going in the opposite direction. We can draw the shear diagram on whichever side of the beam we want, positive or negative. I'm going to start by drawing positive because there's a nice little mnemonic where we try to tell ourselves the story as we go across. So here, the arrow is pushing the shear diagram up by P over 2. We come over here to the midpoint, and now we think about what happens when we go just a little bit past that load at midspan. If we go just a fraction of an inch to the right of it, what is the internal stress, the internal shear needed to keep the left-hand free body in equilibrium? Well, now we have two forces. We have not only the reaction that we've dealt with here all the way up to midspan, but now once we get to the right of that load at midspan, we have a second load. And this is the second force, and this is the load P that we've applied to it. So if you think about it, we now need an internal stress, an internal shear that reflects the difference between P over 2 up and P down. And what that's going to be is P over 2 again, but in the opposite direction. Right now we have P over 2 up minus P, so the internal stress, the shear, is going to be negative P over 2. Okay, to go back to our mnemonic, here's the way the story works. P over 2 pushes the diagram up. We come across, we hit P, and that load pushes the diagram down. And P over 2 minus P equals minus P over 2. Okay, now every slice from there all the way to the other reaction is going to need the same internal stress, the same internal shear to balance these two external forces. So the internal stress, the internal state of shear all the way across is going to be negative P over 2, right? Equal and opposite to the stress, the shear on the left side of the beam. And when we reach the second reaction, notice that it has a magnitude of P over 2. It is going to push the shear value back up to 0. And that, when you think about it, is exactly what we want, because if we go to the right of the supports, obviously there can't be any shear because there is no beam. So the shear diagram always starts at 0, gets pushed up or down depending on which way the loads are going, and always returns to 0. And this is literally the way we will draw these. We will think through what the external forces are doing to the shear diagram, and we will then use that to figure out what the state of shear is within the beam all the way across. So, simply supported beam with a load at midspan will have P over 2, right, throughout the entire beam. That will be the shear stress throughout the entire beam. On one half it's positive, on one half it's negative. The material of the beam doesn't know whether it's positive or negative. All it knows is that the infinitely small slices of its material are trying to slide past one another, right, or resisting that tendency by going into stress, by going into shear. Okay, now let's think about bending, right? What is bending? Well, if you think about literally what it is, when a beam gets bent, you are pushing the top of the beam together, putting it in compression. You are pulling the bottom of the beam apart in tension. This is the result of an internal moment that is going to match the external moment that's being applied to the beam by the forces as we go across. What does that mean? Okay, let's take our infinitely small slice again on the left side of the beam. And when we were talking about shear, where we took that slice didn't really matter. We could take that slice anywhere before the next external force acting on the beam and be pretty confident that the shear in the beam would be equal and opposite to whatever the reaction was here. When we're thinking about bending, we need to think about where the reaction or where the load is in relation to the slice that we're taking. So we look not only at the external force, but we also look at the distance from that force where we're taking the slice. And not surprisingly, when we think about the magnitude of an external force in pounds and the distance from that force in feet, we'll get a figure in foot-pounds, right? An internal moment, a condition within the beam that's able to resist the moment that's implied by that external force around whatever its moment arm is. So here, if we come over, say, 2 feet from the end, we'll have an external force. We've already probably calculated for shear, but the internal moment at that slice will be equal to the magnitude of the external force in pounds or kilograms multiplied by the distance we are from that force. If we go over 2 feet, it'll be 2 times the reaction. If we go over 4 feet, it'll be twice that, et cetera, et cetera, et cetera. This internal moment is something that we will resist using both the tensile and the compressive capacity of the beam's material. That gets complicated. We'll spend a whole set of videos on it in the next week. For now, all we're interested in knowing is that the tendency of that external force to rotate our free body, the little slice of the beam that we've taken, has to be met by an internal moment, right? A twist that's actually within the beam that's pushing back or that's twisting back. If we go to the midspan, we have a much greater distance from the force. And what we find is that as we go across the beam, that external force will impart a greater and greater moment the further we get from it, until the midspan, it's at its peak, much, much larger internal moment. For our beam, right, that load, the load that we're putting on it at midspan, then starts to counteract the internal moment that's needed to resist the increasingly far off reaction, and we'll see the moment come back down, in fact, to 0. So think about, again, what's happening at every slice along the beam. We have a reaction that's P over 2. The further away we get from the support, the longer the moment arm that reaction has around our slice, and therefore the greater the moment will be. So the moment diagram on the left-hand side of the beam is going to look like this. If we are at 0 feet from the support, then our moment is P over 2 times 0, which is 0. The second we have any moment arm or lever arm, the second we move it any distance away from that support, this reaction will start to induce a moment, and the beam will have to have an internal moment to resist that. When we get to midspan, here the moment will be P over 2 times span over 2, right? Half the span. But once we get past our load, what we find is that the external load at the midspan will also start to induce a moment. And notice that it's going to go in the opposite direction. Here, P over 2, we're turning clockwise around our slice. Here, P, as we move to the right, is actually going to be twisting counterclockwise, anti-clockwise. And because it's twice as big, it's going to actually reverse the direction of the moment diagram. And what we'll find, not surprisingly, is that by the time we get all the way over to the other support, the total moment here is going to be P over 2 times the span minus P over half the span. If you add all those together, you'll come back to 0. You can also think about this in the opposite direction, right? We could start taking our slices from the right reaction and move our way left. And as soon as we get any lever arm between the slice we're taking and the reaction here, we'll get the equal and opposite buildup of the bending moment within the beam. So we know now about this beam that it is equally stressed in shear across its length, but that its moment is greatest at the midpoint where it's being loaded. We also know that the quantity of that moment is going to be P over 2 times L over 2. This is a triangle, and we can find the height of the triangle, which is the moment essentially. Or in this case, we can just do a simple thought experiment, right? P over 2 times L over 2, that is going to be the total moment for the reaction of that magnitude times the moment arm of half of the beam's span. So this is our shear moment diagram for this simple beam condition. Shear we talk about we call it V, and moment we call M. And for a simply supported beam loaded in the middle, the shear is going to be equal throughout, but notice that it's positive on one side, negative on the other. Moment is going to get greater and greater and greater until it gets to the center, and then the effect of the load kicks in and it gets less and less and less and less and less until it gets to the support on the right. Now, here's where things get kind of beautiful. Because we're looking at the same magnitudes of forces, and in the moment diagram, all we're doing is adding or multiplying by a figure of length, the shear diagram and the moment diagram are related to one another. The value of the shear diagram, right, so the distance between the shear diagram and the baseline, in this case P over 2, is always going to be equal to the slope of the moment diagram. What do I mean by that? Well, this shear value we said was P over 2. And here we find that the slope of that is also going to be P over 2. That as the moment gets greater and greater and greater and greater, it increases at the rate that is indicated by the shear diagram, right? That every inch we go over to the right is going to be P over 2 times an additional inch. And P over 2 is actually going to be the slope. We can also see this in terms of the sensibility of the slope. So here, notice that we said the shear was positive. Here, the shear is negative. If you look at the moment diagram, the slope of the moment diagram is positive going up here. And then where the shear diagram crosses the 0 line and becomes negative, the slope of the moment diagram becomes negative as well. Okay, next interesting thing. The value of the moment diagram, the height of that line, is because it is related to the value of the shear multiplied by the distance. The value of that is necessarily going to be equal to the area of the shear diagram up to that point. So if you think about the highest point here, and we'll always be interested in finding the maximum moment in a beam, what is the area of the shear diagram up to that point? Well, it's P over 2, right? That's the height of the box. We get that from the reaction there, times L over 2, right? Half of the span. that will be the value of the moment diagram. We'll run some numbers in the next video where you'll see this showing up again and again. We'll go back and we'll calculate the area under the shear diagram and figure out what that means for the moment diagram. And most importantly, notice that because the shear diagram gives us the slope of the moment diagram, we can always find what are called inflection points. Wherever the shear diagram crosses the 0 line, the slope of the moment diagram changes. In this case, from positive to negative, could be from negative to positive. In either case, that moment is going to indicate at least a local peak or valley. And that will tell us something about where the maximum moment might occur in a beam. There are some other kind of fine points that we'll look at as we go through some examples. If all of this seems a little bit abstruse or a little bit confusing, don't worry. When we throw some numbers at it and do some actual shear moment diagrams, you'll start to see that we can rely on these 3 principles to do a lot of the work for us, to figure out kind of a lot of the math behind these. When we step up and do distributed loads, remember that when we were finding beam equilibrium, we were treating distributed loads as concentrated loads. That's fine for finding the reactions, but think about how important it is to think about distributed loads as actual distributed loads when we're trying to figure out what's going on in the beam. If we start taking our slices from the support toward the center, what we find is that every little bit of that distributed load starts to counter the internal shear that develops from the reaction. So here we might find that the reaction pushes us up a certain distance, but right away as we start to build up that distributed load, every little bit of that is going to start to push the shear diagram down. And the shear diagram for a distributed load is going to look like a bow tie. Here we have the reaction pushing the shear diagram up, and here we have an infinite number of infinitely small arrows starting to push that shear diagram down. And by the time we get all the way over to the right-hand support, that distributed load will have moved the shear diagram down to exactly whatever the reaction is here on the right. Now, what does this mean for the moment diagram? Remember that the value of the shear diagram is equal to the slope of the moment diagram. So notice here that we have a very big positive number that gradually decreases. We have an inflection point, the same place we did before, right at the midspan, if this is an equal, fully distributed load. And then notice that the slope becomes negative and gets more and more negative as we go toward the right support. This is the slope diagram for a gentle curve. And the moment diagram for a beam with a distributed load on it will look like a gentle curve with an inflection point again at the middle. There will be no bending moment at the ends, at the supports. If we take our slice an infinite amount to the right here, an infinitely small amount to the right here, neither of those have any moment arm to cause the free body to want to rotate. When we get up to the top, we have the maximum moment. And this is because we are as far away from the reaction from one of the 2 reactions as we can get, and we only have half of the distributed load to counter it. So the maximum bending moment in a beam with a distributed load, also at the middle, but with a slightly more interesting moment diagram. Here, note that there are a lot of things that are happening at the midspan, right? The inflection point, shear equals 0, bending moment is at its maximum. Notice also, Murphy's law says this is always going to be the case. Where we have to worry the least about shear, we have to worry the most about moment. And where we have to worry the least about moment, we have to worry the most about shear. Right? This will happen again and again and again because of this interaction between the 2 diagrams. Okay, that is a brief introduction to shear and moment in beams. It's a lot to throw at you in one video. In the next video, we'll go through a handful of increasingly complicated or increasingly interesting, depending on your point of view, beam loading conditions. and we will look at what the shear moment diagrams for each of them are, and we'll see how closely we can calculate the actual shear, actual moment, and where along those beams we're going to be most interested in figuring out what those are.